In example 3, we are estimating the limit numerically. Now, in example 2, we saw that we could have just plugged in the values. So why don't we try that here? We want to know what's happening to this function as x gets close to 0. So if I plug in 0, let's look at what happens. I'm going to have 0 over 0 plus 1 minus 1. So I'm going to get 0 over 0. No, we can't have 0 in the denominator. So this is a case where you try plugging in the number, but you don't get an answer out. And this is where we need to use limits if we want to find an answer to this problem. Now, it wants us to do it numerically, so we're going to go to Desmos and type it in. So here I'm at Desmos, and I typed in the function, and then I went to add a table, and then I put this table in, and I called the first column x, and then the second column I put the function. And then what our goal is to get close to 0. So I'm putting 0 in the middle. And what we saw by plugging in 0 just a few seconds ago is that we get an undefined answer. We don't have an answer. So what we're going to do is get close to 0 from the left and from the right, meaning smaller and bigger than 0, and see what happens to the y values. So let's think of a number close to 0 that's smaller. I think a close number would be negative 0.1. 0.1 is pretty small, and so that should be close to 0. Well, what if we get closer? So let's try negative 0.01. And then let's get closer than that, negative 0.001. And so we can see as we get really close to 0 from the negative side, the numbers are going up towards 2 because we've got 1.9, 1.99, 1.999. Well, let's see what happens on the other side of 0, because for limits we have to see what happens on the left and on the right. So if I tried negative 0.1, let's do positive 0.1. And closer to 0 would be 0.01 and 0.001. And we can see from the right side, or from the numbers larger than 0, they're also going towards 2. They're getting smaller towards 2. So I've got 2.04, then 2.004, 2.0004. So we're getting really close to 2 from both sides of the equation. So even though I don't have an actual answer at 0, it's undefined for the function, the limit is still 2. The numbers are going towards 2 even though they don't ever actually reach it. So numerically, my answer is 2. So I wrote out my table. This one I did different numbers. So if you want to use our Desmos numbers, you can. But we see that we got really close to 2, so the answer is 2. If we look at the graph, it's not that visible on Desmos, but if you were to look at it, because it's undefined at 0, there is this open point. We call that a hole in the graph. So everything is defined except at 0, we have a hole. But if you look at it, the left side of 0, so this side, the curve is going up towards the 2, even though it doesn't actually reach it. And the right side of the graph, it's going down towards the 2. And so we see from the left and from the right, the y value is 2, so that is why the limit is 2. Example 4, we have that same case again, that if I plug in 1, I'm going to get 0 in the denominator, and so it's not going to give me an actual solution, but instead I can still find the limit. Let's go to Desmos instead of this graphing calculator. Now, if you want to use a graphing calculator, I can show you how to do that in class, but everyone should have Desmos on their computer. So if we go there and type, so I typed in my function and I created a table, and since the limit says I'm approaching 1, I put 1 in the center of my table, and I want to see what the y values are doing to the left and to the right of 1. So we're going to pick x values to the left and the right of 1. Something smaller than 1 that's a tenth away would be 0.9, and something larger than 1 would be 1.1. And we're going to get closer. So I see at 0.9 I'm at 1.81, and at 1.1 I'm at 2.21. So I'm assuming it's going to get closer to 2, since 1.8 and 2.2 are on either side of 2. But I'm going to get closer and try 0.999 and 0.99. And then I'm going to get closer on this side by doing 1.01 and 1.001. And I can see As the numbers increased towards 1, the y values increased towards 2, because I have 1.98, 1.998. And then as the x values decreased towards 1, the y values decreased towards 2. I've got 2.2, 2.02, 2.002. So we're getting really close to 2, and so I'm going to say my limit is 2. 5, we are using a graph to find the limit. And so first of all, this is a piecewise function, and I'd like for you to think about how to graph that before you watch me do it, because this is something I want you to be able to graph on your own. It's not necessarily something we could type in Desmos. We probably could, but you might have trouble typing it in. So what this function tells me is the value of the function is always 2, but sometimes it's 0. So maybe I shouldn't use the word always. It's usually 2 when all the x's are not 3. Now, if you think about all the x's possible for a function, there's an infinite number of x's, but they're saying the only time it's not 2 is when the x value is 3. So that's why I mean it's usually 2, except at 3. And when it hits 3, the y value changes to 0. So the y value is 2 when all the x's are anything but 3, and it changes to 0 when the x is 3. So that means I've got all the y values are up here at 2 for all the x values that are not 3. So I put a hole at 3. It's always 2 except for at 3. And then at 3, the answer is 0. So at 3, we put a filled in point at 0. That's what it actually is. And so that's what the graph looks like. If I use this graph to find my limit, what I see is as I get close to 3 on the left side, so as I go towards 3 on the x-axis, what are the y values doing? The y values are going towards the y value 2. And as I get close to 3 on the x-axis from the right side, if I look at what's happening in the function, the y values are getting close to the value 2. So even though the function value is 0, the y values were going towards or were approaching 2. So if this side goes towards 2 and this side goes towards 2, then the limit is 2. And so we will say that the limit as we went towards 3 on the x-axis, the function values went towards 2, so the limit is 2. In example 6, we're finding limits by direct substitution. Direct substitution, in other words, is just plug it in. So if I plug in 4 here, I've got 4 squared, the limit is 16. If I plug in 4 here, there's no input variable, so the answer is just 5. If I plug in 4 here, I get 16 and 8 minus 5, and if we put those together, we get 19. So that's the limit. This is the same thing on top. See? So if I plug in 4, I get 19. And if I plug in 4 down here, I get 3, so 19 thirds. And so those are the limits. And looking at what we just did, we can write some properties down. If there's no input variable and I just have a number b, then that is like part B here, where if there's nothing to plug in, then the limit is just the constant, so b. If I do have an x value where I can plug in c, kind of like a and c and d, then you just get whatever the number is when you plug it in. So if I plug in c in for x, I get c. If I plug in c for x here, I'm going to get c to the n, or whatever the exponent is. And if I plug in c here, I'm going to get the radical c, whatever the radical is, with c plugged into it. We also have some properties where if you have a limit of a function times a constant, you can bring that constant out front and plug in your c. So they've given you two answers. They said the limit of f as x approaches c is L. And so we can just get that b out of the way, and then we've got that limit as x approaches c of f. And so the answer is L, but there's a B, so it'll just be BL. Here we've got the limit is approaching C, just like both of these are. And we've got F plus or minus G. So the limit of F is L and the limit of G is K. So the answer would just be L plus or minus K. So you can do a limit of that plus limit of that. Kind of, in other words, kind of distribute your limit there. With multiplication, the same works. If you've got limit of that and limit of that and you're multiplying them, you just multiply their answers. So L times K. Same thing with division, L divided by K. And then here, if we've got an exponent, that'd just be L to the exponent.